Okay, so up to this point, we have been talking about electrical forces qualitatively. So, attraction or repulsion, larger forces and smaller forces, and so on. But you will probably not be surprised to learn that there is, in fact, a quantitative law for how electrical forces work. Okay, so this law is called Coulomb's law. And the basic idea is suppose we have two charges. I'm going to draw positive charges here, but they could be any combination of positive or negative, and I'll call this one 1 and this one 2. Okay, so if I want to calculate what the force is on one of these charges, let's say I want to calculate the force on 1 by 2, then the formula for that is K Q1 Q2 over R12 squared R12 hat. Okay, so what are the parts to this expression? So F12 is the force on 1 by 2. Okay, that's my notation for this. And Q1 and Q2 are the charges of object 1 and 2. Okay, so we'll talk about how we can quantify charge in a moment, but we can measure the amount of charge that's present in each case. And then R12 is defined to be the position of 1 relative to 2. Okay, so that's kind of a peculiar notation, possibly. So if I want to express where is 1 relative to 2, then I draw a vector from 2 to 1. Okay, so that's R12, points to the left in this case. And then based on our experience with electrical forces, we expect the two objects to repel. So the force on 1 is going to be away, so to the left, like so. All right, so we can see in this case that R12 and F12 are in the same direction. Okay, so that's why the R12 hat is the direction that's associated with the F12 vector. Okay, well, let's just check briefly whether this law, Coulomb's law, makes sense. So if I increase the magnitude of either charge, so I just have more charge in one of those spaces, then the force increases. Well, I think that seems sensible enough. If I increase the distance between the charges, the force decreases. Okay, we've seen that that is true. If one of the charges is negative and one is positive, then when I plug in a negative charge for one of those two forces, then I'm going to get a minus sign overall. So K is a constant we haven't talked about yet. The charges can be positive or negative. The distance is going to be positive. So the signs of the charges will determine whether this expression comes out positive or negative, and that will tell us then whether we get an expression that aligns with R12 or opposes R12. Okay, so if Q1 and Q2 have the same sign, then the force is going to be parallel to R12. If they're opposite signs, then they'll be anti-parallel or opposite. Okay, so this is kind of cool. By plugging in positive or negative numbers for the charges, we get the sign to work out correctly for this law. Okay, so what else appears in this expression? Well, K is a constant, so K is equal to 8.99 times 10 to the 9th newtons Coulomb squared per meter squared. Okay, and you can check that when you plug in the values, this should work. Actually, I've gone and made a mistake, so it's going to be Newton meters squared, or Coulomb squared, because when I plug in the distances into the equation and the charges into the equation, the meters and the coulombs will go away, and I'll be left with a force. Okay, so this constant has a name. We call this the electrostatic constant. And it shows up in a variety of different places, although we often will write it in a slightly different way, which I'll get to in a little bit. Okay, so you're familiar with newtons, you're familiar with meters, but the coulombs are new. Okay, so a unit of charge in the SI system is a capital C, which stands for coulombs. Okay, and coulombs are named after a physicist. So Coulomb's law is named for the same person that the charge unit coulombs is named for. Okay, so a detail about the way you write out these expressions is that even though the Coulomb is named for a person, when you write out the full unit, you get a lowercase value. That's true for any units in the SI system. So you write out newtons, it's a lowercase n. You write out, volts or watts or any other thing that's named after a person. You always write it out lowercase, even though the unit itself is a capital C. So that's the most common unit of charge that we talk about in this class, because, like I said, it is the SI unit. But there is another very common unit of charge, and that's the electron. So the electron is a lowercase e. Okay, and the relationship between coulombs and electrons is that one electron is equal to 1.6 times 10 to the negative 19 coulombs. Okay, so it takes a large number of electrons to add up to 1 coulomb of charge. In fact, a coulomb is actually a very, very large unit of charge. Very rarely in real life will you ever have a full coulomb of charge. We'll often be working with nanocoulombs or some other really small fraction of a coulomb. Okay. One kind of peculiarity about the unit of the electron is that it is in fact a positive unit of charge, even though electrons are negative. So that's sort of just an unfortunate fact of how we think about these units. Okay, so if you want to talk about the actual charge that a physical electron has, then one electron has a charge of minus E. Okay, so again, it's just kind of a way that we talk about the units, and it's a little confusing, but just keep in mind you have to put in the plus or minus sign explicitly. Okay, so if we want to calculate the net force on an object, if there are multiple charges present, let's say we have a charge over here, which I'll call charge 0, and maybe we have a positive charge up here, and a negative charge over here, and maybe I'll have a really big charge over here, and maybe I'll have a charge that's really far away over here. Okay, so I'll call this one 1, 2, 3, 4. Okay, so we can figure out each of the forces pairwise. So to figure out the force on charge 0 from charge 1, well, I know it'll repel, so there will be a force this way. So that'll be F01. For charge 2, it's actually going to attract, so we'll get a force this way, the force on 0 by 2. For charge 3, it's going to repel, and it'll repel a lot because it's big, so I'll have a force like this, F03. And then charge 4 is going to repel, but it'll be a smaller force because it's further away. So F0, 4. So if you want to find the net force that is on object 0, then what you want to do is add up each of those other forces. So F01 vector plus F02 vector plus F03 vector plus F04 vector. Okay, so you would split each of those into components and then add up all the x components, add up all the y components, and then get the total force. Okay, so the big takeaway from this is that electrical forces are calculated pairwise. Okay, so if we want to know the forces on object 0, we calculate each of the forces on object 0. If we wanted to know all of the forces on object 1, we would have to calculate the force on object 1 by 0, by 2, by 3, and by 4, and then combine those all together. Okay, so there's one other detail I want to talk about for Coulomb's law, and that is the units. So for the electrostatic constant, sometimes we write this a slightly different way. So sometimes instead of k, we'll use 1 over 4 pi epsilon naught, which means that Coulomb's law becomes 1 over 4 pi epsilon naught q1 q2 over r12 squared. Okay, so again, the directions would work out as before. So you might wonder why we would do that. Well, sometimes this will make the expressions work out nicer. So if we calculate something from Coulomb's law, then sometimes the 1 over 4 pi epsilon naught makes a lot more sense. So in this case, epsilon naught is just a different constant, which you can figure out. You can calculate it from k by using the relationship. And it is equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Okay, and there's a name for this constant. This is called the permittivity of free space. And the reason for that is a little mysterious right now. It'll make a little more sense in a week or two, because if we were calculating the force and there wasn't just empty space between the particles, if the particles were like underwater or something, it turns out that the force would be a little different, and by thinking of epsilon naught as a property of empty space or a property of some material, we can then make that sort of adjustment.